Imagine living over 2,500 years ago. No batteries, no smartphones, no power stations. Fast forward more than 2,000 years. The mysterious behavior once observed in amber is now hidden inside almost every electronic device we use. From the moment we wake up until we go to sleep, dielectric materials work silently behind the scenes. Although we rarely see them, dielectric materials are everywhere inside a smartphone. Thousands of ceramic capacitors store and release electrical energy, helping the phone operate smoothly.
A capacitor is an electronic component that stores electrical energy. It consists of two conductive electrodes separated by an insulating dielectric material. When a voltage is applied, charges accumulate on the electrodes, creating an electric field across the dielectric. The red signs represent the resultant polarization of the dielectric, where internal charges slightly shift and form aligned electric dipoles. This polarization enables energy storage, while the dielectric's low DC electrical conductivity prevents direct current flow and reduces leakage. Let's look at the formula for calculating capacitance when there's a vacuum between the plates. The equation is shown like this. Here is what matters. E node is the permittivity of free space, a constant for a vacuum. Is the area of the plates larger plates store more charge? And D is the separation between the plates. Because distance is on the bottom, bringing the plates closer together actually increases your capacitance. Moving on, let's see how we find the total charge stored on the plates. The formula is shown like that. Here is the breakdown. Q node is the quantity of charge stored when there is only a vacuum. C node is the vacuum capacitance we just calculated. And phi is the potential difference, or voltage, applied across the plates. Simply put, the higher the voltage, or the larger the capacitance, the more charge you can pack onto those plates. Now, what happens if we insert an insulating material called a dielectric between the plates? This introduces a new value called the dielectric constant, or relative permittivity, which tells us how much the material boosts our capacitance. Looking at the relationship on screen, C1 represents the new, higher capacitance after inserting the dielectric material. C node is the baseline capacitance we had with a vacuum. Essentially, the dielectric constant is just a ratio. Because this value is always greater than 1 for physical materials, adding a dielectric is a guaranteed way to increase your capacitors over all storage capacity. Let's wrap up by looking at some real-world examples of relative permittivity values and why they differ. As you can see, air or a vacuum sits at a baseline of roughly 1. Ionic solids like salt jump up to between 5 and 10, while polar dielectrics like water have a much higher value of around 80. Ferroelectrics take this even further, reaching into the thousands. The main takeaway here is at the bottom of the slide. Relative permittivity depends entirely on the degree of polarization that can occur within the material. The more easily a material's molecules polarize and align with an electric field, the higher its permittivity value, and the more energy it can help store. Following up on our last point, let's look at the 4 main types of polarization mechanisms that occur when an electric field is applied. As shown in the table, we compare the material's behavior with no electric field on the left versus a local electric field on the right. Electronic polarization involves the shifting of the electron cloud relative to the nucleus. Atomic or ionic polarization occurs when positive and negative ions shift in opposite directions, distorting the lattice structure. Orientation or dipolar polarization happens in materials with permanent dipoles, like water, where the molecules physically rotate to align with the field. And finally, interfacial polarization involves mobile charge carriers migrating and piling up at structural interfaces or grain boundaries. Each mechanism contributes uniquely to the overall dielectric constant of a material. Now, let's see how frequency affects these polarization mechanisms. As the alternating electric field frequency increases from left to right, heavier mechanisms fail to keep up, causing permittivity to drop in steps. Let's trace this graph. At very low frequencies, we see space charge creation or interfacial polarization because mobile charges have plenty of time to migrate. Move up to audio and radio frequencies AFE or F, and polar molecules dominate via dipolar reorientation. Once we reach microwave and infrared frequencies IR, only ionic polarization in ionic solids can react quickly enough. Finally, in the ultraviolet range UV-LWIS, only light electrons can keep pace, leaving electronic polarization as the sole contributor. Put simply, the higher the frequency, the fewer mechanisms can respond, reducing the material's total polarization. Now, let's pivot and look at a direct comparison between conductors and dielectrics to see how their core properties differ. As we break down the table, conductors are defined by the long-range migration of electrons and ions, giving them exceptionally high conductivity. Because of this, they are widely used in current carriers, fuel cells, batteries, and electrode materials. On the other side, dielectrics only allow for small charge displacements, resulting in very low conductivity. This unique ability to hold a field without letting current flow makes them perfect as insulating substrates in mobile communications and, as we've seen, inside capacitors. Let's dive deeper into how these contrasting behaviors shape their engineering applications. Next, let's break down the difference between nonpolar and polarity electrics as shown. Nonpolarity electrics are centrosympatric and have no permanent dipole. Polarization only happens when an external field is actively induced. Polarity electrics are non-centrosympatric and possess a permanent dipole naturally, which gives them a significantly higher permittivity value. In short, polar materials have built-in electrical asymmetry, making them much more responsive to an electric field. Let's take a look at the unique molecular properties of water. As shown in the diagram, a water molecule is nonlinear, meaning it has a bent, non-centrosymmetric structure with distinct positive and negative charges. Because of this asymmetry, water behaves as a permanent dipole. When placed in an electric field, as illustrated in diagram B, these molecules readily realign themselves to oppose the external field. This high polarizability gives water an exceptionally high relative permittivity of 81. This unique characteristic is exactly why water is such an incredibly effective solvent in chemical and biological systems. Next, let's examine a classic ferroelectric material, barium titanate. As the diagram shows, the key to its behavior lies in its crystal structure, where the central titanium ion is slightly off-center. Specifically, the titanium ion is displaced by 0.12 angstroms within its oxygen octahedron. As detailed in the diagram, this permanent shift breaks the structural symmetry and creates a net spontaneous polarization. Because this internal dipole responds so strongly to external electrical forces, barium titanate boasts a massive relative permittivity of 12,000, making it highly effective for advanced energy storage and capacitors. Let's look at the three defining pillars of ferroelectric materials. First, as we saw with barium titanate, they exhibit an extremely high relative permittivity. Second, because of their non-centrosymmetric crystal structures, these materials maintain a spontaneous electrical polarization, even in the complete absence of an external electric field. Finally, the true hallmark of a ferroelectric material is the reversibility of this polarization. By applying an opposing electrical field, we can flip the internal dipoles, creating a distinct and measurable hysteresis loop, which will be shown in later. When dealing with ferroelectric materials, the relationship between polarization and an applied electric field isn't linear, it forms a hysteresis loop. As we crank up the electric field, polarization levels off at saturation polarization. Pull the field back to zero, and the material holds onto a memory of it, known as remanent polarization. To completely wipe this out, we have to apply an opposing force called the coercive field. Now, if we trace how the material behaves under normal conditions, we map out the normal potential path as polarization climbs. Conversely, when driving the field backward to reset or reverse the state, we follow the reverse potential curve, which highlights the material's unique lag effect. To put this in perspective, look at the contrast. A normal dielectric has a simple, straight line response, no memory, no loop. But a ferroelectric material behaves completely differently, tracing out this wide, open loop. This exact capacity to store states is what makes ferroelectric so incredibly useful for advanced memory storage. Now, let's look at some real-world examples of ferroelectric materials. An important property to note here is the Curie temperature, or $T_C$. This is the critical temperature above which a material loses its spontaneous polarization and stops being ferroelectric. As you can see in the table, these temperatures vary wildly depending on the chemical structure. For instance, barium titanate transitions at 120 degrees Celsius, while lithium niobate can handle extreme heat, maintaining its properties all the way up to 1210 degrees Celsius. We also have engineering staples like PZT, where the Curie temperature can actually be tuned by adjusting the composition ratio, X. This flexibility is exactly why these specific materials are widely used in everything from ultrasound imaging to non-volatile RAM. Let's look at how dipoles align in different materials. In the first diagram, we have ferroelectric materials. Here, all the dipoles spontaneously align in the exact same direction, giving the material a strong, permanent electric polarization. Next, in the second diagram, are antiferroelectric materials. Notice how the dipoles alternate up and down. Because they are equal, but opposite, they completely cancel each other out, resulting in zero net polarization. Finally, in the last diagram, we have ferroelectric materials. Here, the dipoles are tilted at alternating angles. Because they don't perfectly cancel out, the material is left with a net spontaneous polarization. These unique arrangements are exactly what make these materials so valuable for advanced electronics and energy storage. Next, let's see what happens when we actually apply an external electric field across a ferroelectric material. This diagram illustrates a process called domain wall migration. Notice the two distinct regions, labeled I and E, where dipoles point in different directions. The boundary separating them is the domain wall. When the electric field is applied, it forces the dipoles along that boundary to flip and realign, causing the domain wall to migrate, in this case, shifting one step to the right. By moving this boundary, the overall direction and magnitude of the material's polarization are changed. This dynamic switching is exactly how ferroelectric materials store data in non-volatile memory devices. Now, let's look at how temperature alters a material's electrical behavior. This graph plots the dielectric constant against temperature, highlighting the critical threshold known as the Curie temperature, or TC, which sits right at 120 degrees Celsius for this material. Below TC, the material is in its ferroelectric phase. It features a high dielectric constant, retains spontaneous polarization, and exhibits a structured, preferential distortion or tilting of its internal polyhedra. But notice what happens when we cross that 120 degrees Celsius peak. The material transitions into the paraelectric phase. The orderly structure gives way to randomized distortions, causing the material to lose its residual polarization entirely as the dielectric constant drops sharply. To mathematically model how the dielectric constant behaves above the transition temperature, we use the Curie law. As shown in the top equation, the dielectric constant, epsilon prime, is equal to the Curie constant, C divided by temperature, T minus the Curie temperature, theta. If we rearrange this equation into a linear form matching the classic y equals mx plus c line equation written in orange, we can plot the inverse of the dielectric constant against temperature. This gives us the straight line you see on the left. By finding the slope of this line, we get the inverse of our Curie constant, C. Extrapolating this line down to the x-axis reveals our Curie temperature, theta, which in real-world materials either perfectly matches or sits just a few degrees away from the actual Curie temperature, Tc. First, a ferroelectric material's crystal structure must be non-centrosymmetric. On the left, a centrosymmetric structure has a center of inversion, meaning positive and negative charges perfectly cancel out. On the right, breaking this symmetry creates the permanent, switchable electric dipole moment required for ferroelectricity. Second, it requires a large cationic size, such as the barium ion Ba2+. With a massive radius of 135 picometers, barium expands the crystal lattice unit cell. This extra space allows smaller, highly charged transition metal ions to easily shift off-center, generating spontaneous polarization. Finally, ferroelectricity can be driven by outer valence lone pair electrons, commonly found in tin 2+, lead 2+, and bismuth 3+. These cations retain a filled outer s orbital 5s2 or 6s2. This stereochemically active lone pair strongly repels surrounding anions, forcing a structural distortion that breaks inversion symmetry. Have you ever heard of relaxer ferroelectrics? Unlike normal materials with sharp peaks and sudden phase transitions, relaxers like PMN feature a broad dielectric curve and high permittivity over a wide temperature range. The secret lies in their tiny polar nanoregions, which provide excellent temperature stability through a diffuse phase transition. We achieve this by swapping out a site or B-site cations to introduce localized compositional disorder. For instance, replacing a site barium with smaller strontium contracts the unit cell, while swapping B-site active titanium for non-active zirconium or tin rapidly drops the Curie temperature, perfectly tuning the material for advanced applications. Can an antiferroelectric material behave like a ferroelectric one? Yes. Take lead zirconate. At low electric fields, it acts as a normal antiferroelectric with no hysteresis loop. But applying a strong positive or negative field induces an antiferroelectric to ferroelectric phase transition, revealing a distinct double hysteresis loop. This fascinating behavior is often driven by hydrogen bonding, as seen when comparing ferroelectric Kh to PO4 with antiferroelectric NH4H to PO4. At high temperatures, both share a disordered paraelectric form with randomized hydrogen positions. However, when cooled, the hydrogen bonds lock into place. In Kh to PO4, the resulting dipoles align parallel to the C-axis for a net polarization. Whereas in NH4H to PO4, the dipoles lock perpendicular to the C-axis, canceling each other out to create an antiferroelectric state. Let's look at some important real-life applications of these materials, starting with two key functional classes, pyroelectrics and piezoelectrics. Pyroelectric materials are non-centrosymmetric crystals that exhibit a net spontaneous polarization that cannot be reversed by an external electric field. Instead, their polarization is highly sensitive to temperature variations. This relationship is defined by the formula delta P equals P delta, where pi is the pyroelectric coefficient. This unique thermal response makes them ideal for infrared sensors and thermal imaging. Next, we have piezoelectric materials. While also non-centrosymmetric, piezoelectrics respond directly to mechanical stress rather than temperature. Under the action of an applied mechanical stress, sigma, they develop electrical charges on opposite crystal faces. This induced polarization is governed by the equation P equals D times sigma, where D is the piezoelectric coefficient. This property makes them essential for things like sonar, actuators, and push-button igniters.
Thank you.